Okay, in this lecture we're going to start our Chapter 3 material on vector-valued functions. And in section 3.1, we will define a vector-valued function and then consider what the geometric interpretation of a vector-valued function might represent in 3 dimensions, which is something called a space curve. So let's start with a definition. We would say that a vector-valued function, or a vector function, is a function of the following form. So these will be denoted as boldface r of t, and we could have a vector function in 2 dimensions. So something of the form r of t is equal to a vector whose components are given by f of t and g of t, or a vector function in 3 dimensions, for which r of t would be the 3-dimensional vector, whose components are defined by f of t, g of t, and h of t. So in short, a vector-valued function, or a vector function for short, is a function which assigns a unique 2 or 3-dimensional vector to every value of t in its domain. So again, a vector function is a function that takes some input value of t and it returns either a 2 or a 3-dimensional vector. Now the functions f, g, and h, which make up the components of these vectors, are called the component functions of our vector function r of t. So in short, again, a vector function is a function which takes some input value of t and returns a vector, either in 2 or 3 dimensions. So to start working with vector functions in a simple way, let's look at evaluating a vector function at a given input. So in our first example, we are asked to consider the vector function r of t, defined by t squared minus 1, and t cubed plus 1. And we're asked to find r of 0 and r of 1. So just like we would for a typical function, to evaluate r of 0, we would take each of these component functions and evaluate at the given input value of t, in this case 0. So our first component would be 0, the second component is negative 1, and our third component would be positive 1. And r of 1 would be found by evaluating this vector function at t equals 1. So our first component would be 1, second component is 0, and our third component would be 2. So we see that for these vector functions, different inputs for the value of t will yield different outputs, different vectors in 3 dimensions, or perhaps in 2 dimensions. This example was working with a 3-dimensional vector. So in our next example, a problem of interest when we're working with functions of any type might be to determine the domain. So just like we would have for a typical function, we would say the domain of a vector function is the set of all inputs, so that is the set of all values of t, such that this vector function would be defined in terms of a real valued vector. So in other words, the set of all t values such that these component functions are defined as real numbers. So here, to find the domain of this vector function, we need to consider the domain of all 3 of these component functions. So let's start with the first component function, which was the square root of t minus 2. So in order for this function to be defined in terms of a real number, we would need the expression under the radical, that is t minus 2, to be non-negative. Otherwise, we start introducing complex numbers. So here, t would have to be greater than or equal to 2. Now let's move to our second component function, which was the natural log of 8 minus t, which would be defined as long as the argument of this logarithm, that is 8 minus t, is positive. Recall that log of 0 is undefined, or log of negative numbers is undefined. So we need the argument of this logarithm to be positive. Or in other words, t has to be less than 8. And our third component function, 1 over t minus 4, is defined if we do not have division by 0. So this is a rational function, a quotient of two polynomials, which will be defined provided that our denominator is non-zero. So this will be defined if t minus 4 is anything other than 0, or equivalently if t is not equal to 4. So in order for this vector function, r of t, to be defined, we need all three of these restrictions on t to hold. T must be greater than or equal to 2, less than 8, but not equal to 4. So let's see if we can write out the domain of this function as an interval. So here I will say the domain of r of t is the set of all values of t starting at 2, including 2, up through 4, but we can't have t equal to 4, or any value of t which is greater than 4, but strictly less than 8. So looking at the inequalities that we had for restrictions for our component functions, grouping those inequalities together, we say, well, t could be greater than or equal to 2, but less than 8, but we had to omit the value t equals 4. So we're left with the following interval. All right. So let's look at some basic calculus of these vector functions. In our next section, we'll start talking in more detail about some operations that we can perform on these vector functions. But the first one that we'll introduce in this section is a limit. So how would we find the limit of a vector function r of t, whose component functions are given as f, g, and h of t? So this definition says this limit would be defined by taking the limits of these component functions as follows. So we would define the limit of the vector function r of t as t approaches a as the three-dimensional vector whose first component is the limit of the first component function of r of t. The second component would be the limit of the second component function, g of t. And our third component would be the limiting value of the third component function, h of t, all as t approaches a, provided that these limits of the component functions exist. So in other words, to find the limit of a vector function as t is approaching some value, we would just take the limit of each component of that vector function. So let's look at an example of this. Here we're told to consider the vector function r of t, which is a three-dimensional vector function whose components are shown here. And we're asked to find the limit of that function as t approaches 0. So let's consider the limit of each of these component functions as t approaches 0. So here my first component was 1 plus t cubed. So we have the limit of a polynomial, which is continuous everywhere. So our limit would be evaluated by simply substituting 0 in for t. So we have a limit of 1. The limit as t approaches 0 of our second component function, t times e to the negative t, would be found by evaluating this function at t equals 0. Which would give us 0 times e to the 0, which is 1, and then 0 times 1 is 0. And then our last component function was sine of t over t, which is not continuous at 0, so we can't simply evaluate by plugging in 0 for t. We see that if we take the limit of the numerator and denominator, we would have sine of 0, which is 0, divided by 0. So for these limits of an indeterminate form of type 0 over 0, we can apply L'Hopital's rule, which says we would take the limit of the ratio of the derivatives of our numerator and denominator. So taking the derivative of our numerator, we would have cosine of t divided by the derivative of our denominator would just be 1. So we're taking the limit of cosine t as t approaches 0. Now cosine is continuous at 0, so we can simply plug in 0 for t, and we're left with cosine of 0, which is 1. So the limit as t approaches 0 of our vector function, r of t, would be the vector whose components are 1, 0, 1. All right. Now we can define what it means for a vector function to be continuous at a point based off our definition of the limit here. So we would say that a vector function r of t is continuous at a value t equals a if the limiting value of r of t as t approaches a is equal to the value of the function r at t equals a. So it follows, based off the definition of the limit of a vector function, remember we're just taking the limit of each component, that this vector function r of t is continuous if and only if its component functions are all continuous at t equals a. So in order for a vector function to be continuous at a value, all of its component functions must be continuous at that value. And if any one component function is discontinuous at a value, then we say the vector function is discontinuous at that value. So in our last part of this section, we'll start talking about graphing vector functions and what they might represent in space. So let's consider the geometric interpretation, or the graph, of a three-dimensional vector function. So here we will define the set capital C of all points x, y, z in space, such that the x component is equal to f of t, the y coordinate is equal to g of t, and the z coordinate is equal to h of t, as t varies over some interval, is what's called a space curve. Now, the equations that we were using to define this space curve, that is x equals f of t, y equals g of t, and z equals h of t, are called parametric equations of that space curve C with a parameter t. So using this definition, any continuous vector function, r of t, whose component functions are given by f, g, and h of t, defines a space curve, capital C, which is traced out by the tip of the moving vector r of t. So this definition might seem a little confusing at first, so let's think about what exactly a space curve is being defined as and how it's related to this vector function. So let's suppose that we're considering a vector function r of t whose component functions are given by f, g, and h of t. So if I evaluate this function at t equals a, I would have some vector whose components would be given by f of a, g of a, and h of a. So once I find this vector evaluated at some specific value of t, say t equals a, I can sketch its position vector representation in space. So that is, I would sketch the vector whose initial position is at the origin, 0, 0, 0, and its terminal point would be some point given by f of a, g of a, h of a. Now, as the value of t changes, let's say I evaluate my vector function r at some other value, t equals b, well, I would have a different vector, let's say r of b, whose components would be given by f of b, g of b, and h of b. So once I find this vector, I could sketch its position vector representation. Again, I'm taking the vector whose initial point is at the origin, and the terminal point would be some point in space given by f of b, g of b, h of b. So if we consider all of the points which are the terminal points of this vector function r of t, as t ranges between two values, let's say from a to b, I would be sketching out some curve in space. And that curve is what we're calling capital C, and it's called a space curve. That is a curve in 3 dimensions or in space. So here, sketching different vectors, let's say that we were choosing different values for t. If I keep sketching these position vector representations, I'm going to be defining different points on this curve. And as t ranges from a to b, we're tracing out this set of points which would define some curve in 3 dimensions. So this is how we can think about the graph of a vector function. So to get familiar with space curves a little more, let's look at some examples where we're given some vector function and we're asked to describe what its space curve would look like. So in our first example, we're asked to describe the space curve defined by the vector function r of t, which has these 3 component functions. So in order to do this, let's consider the parametric equations of this space curve. So we're looking at the set of all points x, y, z, where x is equal to the first component of our vector function, that is 1 plus t. Y would be equal to the second component function, which is 2 plus 5t. And z is equal to the third component function, which was -1 plus 6t. Now, we might immediately recognize this as parametric equations for a line in space. In particular, our vector function would be the vector equation for a line in space. Here we've just written out its parametric equations. So here we can say the space curve is a line in space, that is R3. And to give a little more description, we can say a point that this line passes through. So a line in R3 passing through the point 1 to -1. So recall, for the parametric equations of a line, these constant values are the x, y, and z coordinates of a point on our line. And we can say that this line would be parallel to the vector. I'll call it v, so this would be the direction vector for our line, which would be given by 1, 5, 6. All right, so here those components of our vector are the coefficients of t in our parametric equations. So we have our direction vector and a point that our line passes through. So we've got an idea of what the graph of this vector function looks like, or the space curve that it represents. So let's look at some other ones. In our next example, we're asked to, again, describe the space curve defined by the vector function r of t, whose components are cosine t, sine t, and t. And the resulting curve that we'll get here, I've already defined as something what's called a helix. So again, to see what this curve looks like, let's consider the parametric equations for this curve. So we're going to take x to be the first component of our vector function, which was cosine t. Y will be our second component function, sine of t. And z will be the third component function, in this case just t. So when I look at these three functions that represent points, or the coordinates for points on my curve, I want to ask myself if there's any relation among these functions. Sort of like what we were doing in our chapter 1 material when we were talking about parametric equations for curves in the plane. So we might recall from that early chapter 1 material that when we have parametric equations involving sine and cosine of t, we could make use of the trig identity that sine squared plus cosine squared of some angle is equal to 1. So for this example, we can say that x squared plus y squared, which would be equal to cosine squared t plus sine squared t, must be 1. And so the curve lies on a cylinder about the z-axis of radius 1. So let's think or describe in a little more detail how I got that information. So when I'm looking at a relationship between the x, y, and z coordinates for points on this curve, I see that the sum of x squared plus y squared is 1. Now in space, that equation, x squared plus y squared equals to 1, would define a circular cylinder of radius 1, which is centered about the z-axis. Since the variable z does not appear in that equation, it's a cylinder centered about that axis, thinking back to our section on quadric surfaces. So let's think about what this z component tells us. Here we have z is equal to t. So as t is increasing, our curve is moving upward along the z-axis, or moving upward from the xy plane. So here we can say as t increases, z also increases. And let's think about what's happening with x and y. So as t increases, sine and cosine of t will be periodic. That is, they'll keep running through the same set of values on an interval from 0 to 2 pi. So z increases, and we can say the circle x squared plus y squared equals 1 is traced in a counterclockwise direction. So let's try to visualize what our curve looks like. And it's this type of curve that we're describing is something called a helix. So let's try to sketch it in 3 space. We have our x-axis, our y-axis, and the z-axis. I'm just going to draw the positive z-axis here. So let's consider the graph of this helix starting from t equals 0. So if t is equal to 0, x would be equal to 1, y is equal to 0, and z would be equal to 0. So I've got the following point on my curve corresponding to t equals 0. And I said that this curve is going to lie on the circular cylinder centered about the z-axis of radius 1. And as t increases, z will increase. So my curve is going to be moving upward along the z-axis. And it's going to be tracing out, in relation to the xy plane, a circle of radius 1, but in the counterclockwise direction. So we get a curve that has this sort of corkscrew shape. And I can indicate the direction of motion along this curve with the little direction arrow. And this sort of curve is what's called a helix. All right. So in our last example, let's consider another problem of describing a space curve. Here we are asked to describe the space curve defined by the vector function r of t, whose component functions are given as t sine t, t, and t cosine t. So again, to get some idea of what this curve might look like, let's consider the parametric equations for this curve. So x would be t sine t, y would be t, and z is t times cosine of t. So as we did with the previous example, when I look at my parametric equations, I might try to find some relationship among certain components or certain coordinates for points on this curve. And for this example, when I look at the parametric equations for x and z, I can see that they both involve t times sine of t or t times cosine of t. So anytime that we have these equations involving sine or cosine of t, we can make use of the trig identity that the sum of the squares is equal to 1. So let's consider evaluating x squared plus z squared. Now x squared would be equal to t squared times sine of t squared. Then we have plus z squared, which would be t squared times cosine of t squared. Or if I factor out a t squared, I'm left with sine squared t plus cosine squared t, which is 1. So my equation is then x squared plus z squared is equal to t squared. So geometrically, this is describing a circle of radius t in the xz plane, or parallel to the xz plane. And we see here by looking at our second parametric equation, y is equal to t. So as t increases, y will be increasing. So a little description about our curve here. We can say that this curve lies on a surface defined by x squared plus z squared is equal to t squared. So some sort of cone shape. If we think back to our equations for quadric surfaces, and as t increases, y increases. So let's see if we can sketch this. It's going to look something like a helix, but with an increasing radius since our surface lies along a cone instead of a cylinder. So here in space, we have our x-axis. I'm only going to draw the positive y-axis, since I'm just going to consider the graph of this thing starting from t equals 0. And then we have our z-axis. So let's sketch this starting from t equals 0. If t is 0, then x, y, and z are all 0. So we start at the origin, and as t increases, we will be moving forward along the y-axis, since y is increasing, and we're tracing out a circle in the xz plane, which will be increasing in radius. So we have a curve that looks something like a helix, but has an increasing radius as t is increasing.